Hello, everybody. Welcome back. Welcome to week 4 of the semester. Okay, so let's see, where are we? You've done exercise 2, you're doing exercise 3, great. Quiz 1 is on the horizon. Let's assume I will have emailed you about that, or will soon. I think the short version of what you want to hear is before stats. So like cleaning data and before is what that will be about, unless I say otherwise in an email. Oh, right, one other thing. I've been playing with the style sheet on my slides. There is now a dark mode for everything. I don't myself use it because I'm not a weirdo. But if you're a dark mode weirdo, if there's anything wrong, like if I had to fix a few figures to make them not black on a dark gray background. But yeah, if there's any weird crap, let me know. I'll fix up figures or style or whatever it is. Okay. Now, we were reviewing stats, or like just starting to review stats at the end of last week. So I think this is where I left off. The questions that people have in general, I mean, you know, no universal statement is true, but usually when people are asking a question, they're asking about some population. They're asking like, you know, of how will our customers behave if we put this item on sale? And then, you know, from that you have to narrow down the question and be like, well, okay, you probably are really asking about profit, and then okay, if we put it on sale, we charge less, but we sell more, and how will that trade off? And the answer is I don't know, because the customers that would behave if the thing was put on sale, that population doesn't even exist yet because it's not on sale yet. A more like, you know, silly textbook example, you know, something like, are men taller than women? If you'll forgive the cisnormative thing, I'm aware gender's not binary, but I'm just trying to fit a question on a slide here. Okay, this sentence doesn't make, if you interpret this literally, right, if you're really going to be annoyingly pedantic about this, this statement could mean all men are taller than all women. So if you ever find a counterexample where one woman is taller than any man, the statement is false. But of course, that's not what people really mean by it. They mean something like the average, or like the mean or the median or something. But point for the moment being that statement or question is about the population. We don't get the population. That's not a thing we get to do. You know, I don't get to go and like simultaneously and perfectly measure every human being on the planet to get their height. Or it might be infinite. Or again, like I said in the last slide, this population doesn't exist because they're in the future, a potential future, but we can usually sample. I could put the item on sale, you know, do an A/B test on the website, put the item on sale for 1% of people and see what they do, and take that as a sample of the population, or take this sample of the population. And if I choose the sample well, hopefully that tells me something about the population. Hopefully, if I do everything right. And then the whole game we're playing here, like when doing inferential stats, again, the person who taught me a stats course way back when didn't do a good enough job of sort of nailing down what the heck we're doing with all this. This is all about using samples to come to conclusions about the population, whatever that conclusion may be, because it's usually framed in terms of a random variable, right? There is some probability distribution from which human heights are sampled. Sounds like the wrong word. It's the way human heights are distributed, I guess. Basically, if I choose a human, what's the probability of getting them to be that height? You know, if I measure them accurately and whatever. If I knew this, right? If I knew this probability distribution, I can answer these questions, right? I can come to these conclusions, but I don't get to know that. I know that probability distribution's out there somewhere, but I have to wander around in the dark and try to guess. So probability distributions, like these things that are like, I don't know, like you add like all the numbers are between 0 and 1. If you add everything up, it's 1. And if you have those properties, you'd probably say, yeah, it looks like a probability distribution. This seems fine. People seem to understand this. The way you usually visualize these, I don't know, depending on the vibes and what you're trying to sort of see, usually probability density function is a thing that looks the most reasonable, I guess, to my eye. This thing, right? Like usually I think of a normal distribution looking like this red line. Again, depending on the context, maybe the blue line is a little bit better. It's one is the integral of the other, and one is a derivative of the other. Again, whichever way you like. Again, for me, it's almost always going to be probability density function. Or I guess the sample version of that is effectively a histogram. So then we have this probability distribution that we know is out there, but we don't know very much about. But we can start taking samples and measuring and learning things probably. So both the population and the sample have a mean. The mean of the sample is the thing you think of when I say mean. Add them all up and divide by the count. There's the mean for the population and the mean, again, different notation because it's a different thing. What I'd like to know is the mean of the population usually, or the expected value. What I get to know is the mean of the sample I took. Fortunately, if I do have a good sample and I calculate the sample mean, that's an unbiased estimator of the population mean. So if that's basically to say this, right? If I go around sampling, take the mean of the sample, the expected, of course, that's a probabilistic thing I just did, right? Sampling is inherently a like randomly choose some from the population. So I don't know what this mean is going to be, but the expected value of it is a thing I'm interested in. So X bar and mu are not going to be exactly the same, almost certainly, but I can estimate the thing I care about with the thing I can actually calculate. There's other ways to get, figure out where the middle of things are, median or mode. I'm sure someone's talked to you about this, right? Like the median means something, the mode, the mean means something where there's outliers, and the outliers kind of drag the mean, but they don't drag the median as much. And this is a whole story, right? Fine. And then the question is, well, there's this probability distribution out there. How spread out is it? Is everybody exactly the mean? Or, things are kind of a little bit bigger, a little bit smaller. The standard deviation is the sort of first way to measure that. Like I said when I was talking about Kalman filters, where we're dealing with standard deviations, I think the standard deviation makes much more sense to my squishy meat brain because the units match the data. The standard, like if I'm measuring somebody's height in centimeters, the standard deviation of that distribution is a number of centimeters from the mean. I could square that if I want and call it variance. And once again, I have the thing for the population, sigma, or the thing for the sample that I took, S. And again, I think in my head, standard deviation was just sigma. There's a population one and a sample one. And once again, it is also, it's a good way. Like measuring this for a sample is a useful thing to do because it's at least we expect close to the population. One of the useful things that the standard deviation tells you is what I guess fraction of the population is that far away from the mean. For a normal distribution, well, again, like I said, when talking about Kalman filter, about 2/3 is within one standard deviation of the mean. In general, it's a little bit less, but somewhere in there. So this, right? Where's the middle? How spread out is the data from the middle? These are basically what those two numbers tell us. It's a pretty good, like if I only get two numbers to describe a distribution, that's a good two to choose. So back to computer land. Pandas will do this. So this is the there's a dog rates data from a couple weeks ago, or at least a subset of it. I can never remember if the thing that I have when I did this is the same as the one you got. It's certainly similar. Okay, so the mean rating is 11.76. Fine. Things are spread out that much from it, 1.6 rating units or whatever. Yeah, this kind of makes sense. One thing I will point out, I mean, timestamp is numeric. It's number of seconds after the start of time, where the start of time is probably January 1st, 1970. It might be a number of milliseconds, depending how this conversion happened, depends on the tool. ID is an integer. And of course, as far as pandas is concerned, integers are something they're numbers, you should take the mean and standard deviation of them. I would argue that ID here, if I come back a few slides to types of data, I guess, where was that? The rating and the timestamp are quantitative. I would argue that ID is just nominal. Maybe it's ordinal in that later posts got a larger ID, but like this number means nothing, right? It's a completely pointless value to have there, but pandas does it. Okay, so also something that we saw with a Kalman filter was covariance. And again, this is the version for the sample, the version for the version for the population, version of the sample. And it's basically, do these change in the same direction or in opposite directions, or kind of not in the same way? So if the covariance is positive, I expect them to go up at the same time. If the covariance is negative, I expect when one goes up, the other will go down. If it's 0, I kind of expect them to not be related. But remember, it's a linear relationship. Another thing that I don't think I knew, I don't, like, my brain does not understand what a covariance is. If you say, yeah, the covariance is 17, I would nod and I would say, well, at least that's a positive number, so I have some sense of what it means. But like, I don't know what the scale is that 17 is measuring, right? It turns out you can scale the covariance down into a useful range, -1 to 1, and that's the thing you call correlation coefficient, or whichever one this is, Pearson's probably. And you just divide. The variance by the covariance by the 2 standard deviations, and you get a thing that's totally meaningful. I totally understand what an R value is. It's R for the population. It's rho for the oh, sorry. Should be careful about this. It's R for the sample. It's a rho for the population. Okay, so now I have something I understand. 1 means pretty much just a straight linear relationship. -1 means a linear relationship, but with a negative slope. The 0 means no linear relationship. Remember, it's looking for a linear relationship, not like if it's close to 0, there's nothing going on between these two. I'll do an example in a sec. There's a thing for that, and I don't think you didn't have to look. You did do a stat.linregress, but you probably didn't look at the .r value of it. That's this R value for that sample. So, once again, linear relationship. Well, if you take these points, and again, I promise, real data, real calculation. Well, sorry, I made up data, but real calculation. I took these things, calculated an R value, and it's 0.003. And if you look at that 0.003 without looking at the plot, maybe you would say, oh, no relationship. If you look at this plot and you say there's no relationship between the X and Y, I don't think you know what the word relationship means. It's just not linear. So those summary stats, and again, that dataframe.describe will get a bunch of stuff. Obviously, it doesn't do every possible linear regression, but you can do whatever linear regression you think is interesting. I think a lot of people who haven't dealt with a lot of data think the summary stats tell them like everything they need to know or something. And that's shockingly not true. It's very, very much not true. And I think, again, I don't think I understood, when looking at the stats textbook, why like the plotting library was introduced in chapter 3, because like explaining your results is chapter 17 or whatever. And I thought plotting was about presenting results, and it's really, really not. A plot is the first tool probably to explore data. Possibly Anscombe's quartet convinced you of this. This is data from 1973. This nice statistician created this sample. So this is by hand, right? This is probably has not been done with a computer search. This is Dr. Anscombe or whatever spent some time on this. All 4 of these data sets have the same means, X and Y, same variances for X and Y, same correlation coefficient, same regression line. So if you just looked at the top third of this slide, you might say that these are 4 data sets that are the same. And if you didn't look at a plot, that would be a reasonable conclusion to come to. And the point here is that therefore you have to look at the plot, otherwise you don't know what the heck's going on in your data. If you look at a scatter plot of these 4 things, it's pretty obvious these are not the same. And again, if you look at these plots and you think these are the same data set, we have a problem with the basic idea of what data sets are and what it would mean for them to be the same. Linear relationship with something else going on, perfect linear relationship with an outlier, probably a quadratic thing. And then like x equals 8, except the weirdo, where x is something else entirely. Even drawing this regression line in like 2 of these cases, you're being a little dishonest with yourself, right? Like drawing this line across that data, even though it is the minimum sum of squares line, that line is not adding to this conversation. So if you come across a data set, if I give you a data set, if you don't know what's happening there, you need to plot it. Again, if it's 2-dimensional data, probably a scatter plot's a good way to go, or pick 2 variables that seem to make sense together and do a scatter plot. This, I am told, like, of people who are serious about stats and data, this is absolutely the first thing. Like a friend who works with a biostatistician, it's like, yep, you sit down with the biostatistician and they are, they're typing like plot.plot and doing a scatter plot before the rest of your sentence leaves your mouth, right? It's just the absolute first thing they do. You have done this, right? I made you do this in exercise 2, as I recall. Again, like I can see a lot of what's going on here. You can argue that maybe there's, it's hard to see the data is all like kind of piled up on itself here. Maybe I could do better with this visualization, but at least I see something. I kind of see what's happening here. I am curious, as I record this, exercise 2 is still in the future. So we're not actually coming to a conclusion here, are we, this week? But certainly the slope is positive. Like I don't have to actually do it to be well aware that the best fit line slope here is going to be at least a little bit positive. Is this relationship linear though? I now can sort of see what's going on, and I'm not sure. I guess, again, just on the plot, I can also see this, right? This is a personal failing on my part, where like the Twitter API, when it worked, only let you go back so far, and then obviously I collected data here or something, and then I couldn't get this, and I don't remember why. So there's a hole in the data. It's missing data. It's what happens because I only spend so much time, scraping this data set, and I just forgot for a while and had a gap. For one variable, maybe a box plot. Honestly, I don't know that I've ever drawn a box plot in my personal life. I feel like a histogram is a much more useful thing to do, and much better at sort of getting you again, like human understandable visualization. In fact, I realized, like, I came over here, I prepped some data earlier for stats as we're going to continue, and I did a histogram, and I did it just because how else am I going to explain this data? This is the data. It looks like that. Now you know what's going on. There's a blue data set and the orange data set, pretty similar, and the green data set's over there, a little different. And if you have some sort of color vision problem. My apologies. I'll do my best to make things get some good contrast. So, okay. Once again, this should be stats. This should be a review of stats, but I'm telling you, do a plot. Hint for upcoming exercise. Since we're talking about probability distributions, again, these things that I know are out there, but they're you know, they sort of only exist in textbooks and in theory. I can sample from them, but I never get to see them directly. So how can I come to a conclusion from that? Well, we'll get there. For example, let's say that like anytime there's like a random process, right? You say, well, there's the result is drawn from some probability distribution. So the random process that I might do is I might go and I might measure a bunch of things from group A, and I might measure the same things from group B, and then I might do some very specific calculation, and then I might ask myself, well, if I assumed that they had the identical mean, how weird is it that I found these samples? And it turns out this is a probability distribution for that story. It's if we assume I have two groups with the same mean, and then I do some sampling and I do a bunch of arithmetic that I'm sure was in your stats book. It turns out what I'm doing is sampling from this distribution. So if I end up way over here on that distribution, that seems weird. That seems unlikely. We'll come back to why that, or what that might tell us. The thing that comes up a lot is a normal distribution. It just turns out it just comes up. A lot of stuff just kind of looks like a normal distribution when you start sampling. And again, I don't know if human heights are truly normally distributed. I don't have any like Dede's eye view on humanity. But what I do know is, you know, when you start measuring people, it seems like that kind of shape, histogram. For Kalman filters, we assumed normally distributed noise. So I don't know or care at this part of the story what the truth looked like, but what I did assume was each individual measurement was sampled from a normal distribution, and that normal distribution was centered on the truth. So we had to deal with that, and the Kalman filter did whatever math, you know, shook out of that. It turns out normal distributions are not only quite common, they happen all over the place. One of the places they come up is if you have a large number of discrete samples, independent samples. It turns out a normal distribution falls out as n gets large. It turns out the central limit theorem says there's kind of always a normal distribution hiding in there if you look carefully enough. And we'll come back to that. Okay. Let's do some inferential stats. That'll be fun for everybody. Okay. So once again, the sort of premise here is I don't know the probability distribution because I can't, but the question I'm trying to answer is about the probability distribution. So hopefully what I can do is infer something about the probability distribution based on some samples. Or I guess I might, you know, equivalently say I might do an experiment and then come to a conclusion. That's basically what we're doing here. And all these statistical tests that hopefully you've seen some of, I imagine you've seen some of, are basically for this game. And again, I think we should kind of remember this, right? When you're doing stats, inferential stats, there is this probability of just, maybe it was a coincidence. We should think about that. So we'll come back to this lame, fits on a slide, but everybody understands it question about height. Okay, well, again, if I had some sort of deity's eye view on the situation, I could just actually know, well, fine, but that's not what we're doing here. What I can do is go out there and measure some people, and I can say, well, the men, I had the blue probability distribution, or the blue histogram, and the women had the red histogram, and then I made these numbers. I didn't go I don't love you that much to go out and start measuring people just for a lecture slide. But, you know, I'd probably get something like this. I think they're real means. I did look up in Wikipedia, like the mean height of people, and I did make fake data, at least with the right means. So I know that there is some distribution out there. I kind of suspect it's vaguely normal in its distribution. There's probably a lot more to say about that, but that's another course. But I don't get to see this slide. I get to see this slide. So what we're going to do here, we're going to do a hypothesis test. And I'm going to start by assuming something. That's the null hypothesis. The alternate hypothesis is the like logical negation of that. It's everything else. Usually the thing I kind of want, the thing I'm trying to discover, is that the alternate hypothesis is true. So I start by assuming the thing that I'm interested in is false. So that in this height example, this might be, well, I kind of suspect I'm going to conclude that on average, men are taller than women. So I'm going to start by assuming that they have the same heights on average. This, and again, logical negation of that is the alternate hypothesis. So be careful about that, right? I heard myself say back there, I think that men are taller than women, and then I'll assume that they're equal. But this is not what I meant. This is what I said because it's hard to put these things in natural language. I've got to be careful about this. I could have done the other thing, right? So I did, and this is what I'm going to stick with, this two-sided test where the null is equality and the alternate is different. You can do the other sort of phrasing of this. This is a little fishy. This is, I think, suspicious. Because of course, if I phrase things this way, I'm kind of assuming the conclusion that I think is true. I am designing a statistical test and probably an experiment where it's impossible to conclude that women are taller than men. That is not a conclusion that can come out of this study. So I just assumed which way things were going to fall out. And okay, I have some experience with heights of humanity, but you know, for something like some study where it's like, hey, I'm hoping to find out that this drug helps, that this, outcomes are better if people take my drug. But I really also would like to know if our outcomes only better for the people that don't die or something like that. Like, I really want to examine both sides. And this one-tailed test is, so if somebody comes at you with a one-tailed test, you should be a little suspicious. Just like somebody that really, really, really wants to sell you something really badly, that's probably not a good deal. Well, same vibe with a one-tailed test. It's like a taxi tote outside an airport. Okay, so what we're doing here is effectively a proof by contradiction, which I'm just going to assume that you all nod and say, oh yes, proof by contradiction. We love those in Macam 101. But the game that's being played here is assume the null hypothesis is true, reach a probabilistic contradiction. So look at it and say, well, okay, but if the null hypothesis was true, this whole thing that happened was really weird. So it probably isn't true. So alternate hypothesis. The implication of that is that you can never conclude the null hypothesis in the same way that, like, I'm sure of however many people in this class, probably somebody tried this on the Macam 101 exam, right? It's like, well, I think I'm supposed to do a proof by contradiction. So assume the negative for the contradiction, and then like a page later, you didn't get anywhere. So you're like, well, screw it. I guess the null hypothesis must be true then. Maybe I'll get part marks. But that's not how that works. Okay. Specifically, the t-test, which again, I'm assuming you've done before, but well, again, history tells me you've forgotten. So the sort of premise of this test, we're looking at two populations. So I have like men and women. I don't have like red, yellow, green, or like Vancouver or Ottawa, Toronto, or whatever. I've got two groups. um, that are drawn from a normal distribution, which is all well and good to say, but I've just been going on about how you never get to know the true underlying distribution. And now I put myself in this situation where I have to know, or at least assume, that the true underlying distribution is normal. So I'm in trouble. Okay, let's hope for the best. And again, the question of variance or standard deviation, again, is one of the population, which I don't get to know. But in this story, the null hypothesis is means are identical. So if I falsify that, it means it's the means of the two populations are different. So I get some data. I've got these 30 and 35 data points. And, well, okay. Are they, like, I feel like I'm already in trouble here, right? Normal distribution, equal variance. I could certainly convince myself that these are equal variance if I the histograms kind of seem equally wide. Are they normally distributed? I don't know. I mean, maybe, like the orange looks like it is, the blue maybe doesn't. But what I really care about are the means. Is the blue population or whatever a bigger number of whatever we're measuring here than the orange population? Well, okay, these samples have a different mean, but who cares? Maybe, like if I go out and I measure a couple people, a couple other people, I don't expect the means to be exactly the same. Maybe it's just a coincidence. I just got unlucky. I happened to measure a couple of tall men, a couple of short women or whatever. But I guess that's why we have stats. So I have this story. And I'm going to assume that the means of the two populations are equal and see where that takes me. And like I said, there's this random process that just happened. And the random process is the sampling. Those populations are out there. I sampled 100 here, 50 from this side and 50 from that side, or whatever the numbers are. So what I did was sample 100 individuals from the underlying two distributions. So if I assume this, the question I'm asking is, how weird was this experiment? Like, I got this outcome where I measured the blue group and the orange group, and I got these numbers. Is that weird? Like, if those two populations have the same mean, how likely would it be for this to happen? That's what the t-stat is telling us. And there's some way to calculate a t-stat that was in your textbook one time. I'm just going to call the function for it. That's fine by me. That's why the calculation is what it is, because we can go from the t-stat to the actual number and get a probability. The one thing I probably should keep an eye on is what goes into the t-stat. Like, what's it all about? And because the number of samples matters. If I have more samples, it will be easier to come to a conclusion. What are the means? If the means are farther apart, it will be easier to come to a conclusion. If the variances are smaller, it will be easier to come to a conclusion. So maybe I should develop a little bit of like instinct here about like, well, if what am I going to say here? My theory is that like small cars and large trucks get different fuel economy. And then, like if I suspect in that case, like one of these numbers is double the other number, those are pretty far apart. It seems like it should be easy to come to a conclusion there. But for something like this specific small car and that specific small car get different fuel economy, well, those means are going to be very close together. It's going to be much harder to come to a conclusion. Maybe I am going to need more samples to get there. There's a whole question of like experimental design here that is not one for this course. But anyway, I got my picture back here. Well, I've got my data that gave rise to this histogram. I shook it around, threw it through the t-stat calculator, and I got this. What does that mean? Well, I have this picture. This is the t-distribution, or the probability density function of the t-distribution. I'm over here. that's weird, right? It's weird, like if I'm truly sampling from this distribution, which assumes the null hypothesis, I would expect, you know, a 1 or -1 or 0. Like I'd expect my experiment to produce a t-stat somewhere in the middle. It didn't. It's way over here at 2.4 whatever. And then there's about, I'm going to pronounce this 1%, if you'll forgive me. There's 1% of the area under the curve is over here. And then, of course, the experiment could be weird in this direction. It could be weird in the other direction, like the blue is bigger than the orange and the orange is bigger than the blue. So it could be equally weird off on this side. So it could be the other 1% that's equally weird. So I put those together. I get about, again, this is if I assume the null hypothesis, I do this experiment, there's only about a 2% chance, 2% probability of getting something as weird as this outcome or weirder. So it seems like it's really unlikely that this happened. This doesn't sound like what I would expect out of an experiment. I would expect something closer to the middle. So what I'm about to do is a proof by contradiction in my head and say, well, this makes it seem like my assumption is false. That was a null hypothesis. Therefore, I will conclude the alternate hypothesis. That's the game that's being played here. And with all inferential stats, it's, I have done an experiment. I'm assuming the null. Oh, you hope that you come to this point of saying, oh, geez, that's really weird then, right? It's really crazy that this is the outcome of my experiment if the null hypothesis is true. So probably it's not. Probably my means are different for a t-test. That's all. So do y'all still, like, I feel like for shockingly long, the way that you did this was calculate the t-stat by hand and then go to the back of the textbook. Do y'all still do that? I feel like please tell me this time has passed. Anyway, the way I do a t-stat, well, actually, no, I don't care about the t-stat. The point of the t-stat is to give you something to look up in the back of the book. I care about this. I care about the p-value, which is that, again, what's the probability of being this weird or weirder, assuming the null? Okay, well, let's try it. Like I said, I got some data over here. Well, I guess I know, again, because I'm completely cheating, I do know that these are sampled from a normal distribution because it's just fake data sampled from a normal distribution, but usually we don't get that luxury. But I do that, and then I can say that. So that's the t-test of independent whatevers. So the p-value is, oh, so this, the display of this has changed. Okay, so that's times 10 to the -5. It's really weird. It'd be really weird to get this distribution of data if the means are the same. Probably not. If I slide those a little closer together, oh, and maybe I don't need, I'm not using the Z data, so I don't need it. This is not weird. This is a totally reasonable thing to happen. If these had the same mean, this is kind of the outcome I would expect. So I cannot conclude anything. Right? There's no conclusion here. One thing I will just point out here, this np.float, this is Python's representation. I'm sure these nice people have explained it. Repr is kind of meant to be the programmer friendly output, I guess, and the string is meant to be a little more human friendly. So this is the internal representation. If you print a value, you get the more friendly version. So these are the exact same thing, just different string representation of them. Don't be alarmed. So yeah, I wouldn't usually print in this context because well, why would I? I'm a programmer. I'm happy to take the programmer friendly output, but that's what's going on there. So I've got this p-value that is effectively encapsulating the weirdness of the situation if the null. So if that t-stat is low, if it's close to 0, I will say the null must be false and therefore for a t-test, the means must be different. Yeah, I've assumed a little bit here, right? Normally distributed equal variance. I do have equal variance here, but if I didn't, it's not like an exception gets thrown, right? It will still do the thing. Wait, let's make this a little more differenter. So now if the mean is slightly different, okay, well, how do I trust this p-value or not? And there is a little bit of question there. So far, yeah. So what we're looking for here is this p-value. If it's small, we say the null hypothesis must be false. The verb there is reject the null. And therefore, I'll go to the alternate hypothesis and say, there's my conclusion. If the p-value is large, I say, I didn't learn anything. So here's the danger. And there's a lot of like weird danger in stats that's just like, it's tempting to, you know, when you're like, because yeah, I have a conclusion I want here. I want these to be different because presumably that's the experiment I'm running. That's small. It looks pretty small, right? And I really want to conclude that the means are different. So therefore, I'm going to conclude that's small. But no, like we have to be honest with ourselves and with our readers here about what that is. Like, what's our cutoff going to be? And our cutoff is going to be alpha. And for this course, alpha is going to be 0.05. If you're being really careful, sometimes people will take alpha to be 0.01, but for us, 0.05 seems fine. And remember, there's a probability of failure. Like, there's a probability of just do an experiment, and just by complete chance, you get a small null hypothesis. That's literally what the p-value, or you get a small p-value, sorry. That's literally what the p-value is for. Yeah, this seemed really unlikely. But sometimes unlikely things happen. That's how probability works. So we'd better remember that. Again, be honest with yourself and others. So like I said, if the means are more different, if your data set is smaller, it becomes harder to come to a conclusion. That's just the way the math works out. So yeah, where I had 100 and 120 points, a hugely small p-value with a smaller data set, even though they're sampled from the same distribution, a much larger p-value. That's how, and again, that's just how the t-stat is calculated. The things that go into that take this into account. So this will happen. Yeah. Once again, I have two ways that an experiment here, or the two ways I guess a test can end up. One of them is small p-value reject the null, and therefore the alternate is what we've decided is true, or nothing. No conclusion here. So like I said, we're like in trouble from the start here, right? Where I have to promise the t-test these have been drawn from a normal distribution, and this is not a thing I know. It's not a thing I can know. I can look at the histogram and say that looks kind of like a normal distribution, and of course the equal variance. I can look and say, well, it looks like the data in my experiment has a pretty similar variance. I can calculate it and look at it. Maybe I should. Maybe I should remember. Is this how you spell that? Yeah, right. I guess I do know the standard deviation. The standard deviation of the population was 2. Okay, so like, are those the same? Like, it looks like my y values have a smaller standard deviation, right? What do I do with this? The first thing is the tests are reasonably robust. That, you know, if I have two data sets that are ever so slightly not exactly that distribution, it's fine. Like the p-value is not suddenly meaningless as soon as things are ever so slightly different. They're pretty calm to this being these assumptions being slightly wrong, so statisticians tell me. But I have to be at least a little careful here. If I have, I don't know, something like that, this thing where, I don't know, that's probably not a normal distribution anymore. I mean, I should do the same thing to both so it looks like the same picture. You know, it still looks kind of like I have more right tail here, but it still, geez, it still looks like a normal distribution, doesn't it? Math's crazy. I have to be, so for the moment, the watchword is we have to be careful. These are the kinds of things we're going to see assumed in statistical tests. I think the first two are really like good experimental design. Again, if I'm just doing the, like, again, the men are taller, the men and women have different heights question. I mean, if I'm doing this, if I walk out into the AQ or whatever and I start measuring people, well, what if, I don't know, are SFU students taller than normal people or shorter than the population? And I don't know, maybe. Y'all probably got on average better childhood nutrition than like the world on average. I don't know. Maybe I should think about that. Independent, identically distributed. This is, again, one that it's easy to just say it in a stats textbook and whatever, but this is something like, if I'm measuring people in the AQ, well, probably like a group of people are all going to come by and they're all going to let me measure their height at the same time. Maybe tall people have tall friends, or maybe like the, you know, the basketball team is walking by and then I got non-representative, and also that those 5 people or whatever, their heights are sort of not measured from the same distribution because the basketball team doesn't have the same height distribution as the rest of humanity. I've got to be careful about that. You're going to see this, actually, some of you are going to see this in exercise 5 or so. I'm having you like run an experiment of like run this code a bunch of times and see what happens. If you have a laptop that doesn't have really good thermal management, your processor can overheat and throttle itself back and slow down, which basically means the first half of your tests were not drawn from the same distribution as the second half, because the second half were basically run on a slower processor. So like, I do have to think about these things. This matters, but if I've done a good experiment, we should be okay. So that's a good spot to take a break. See you in a few minutes in part 2 of this week's video. We'll pick up from there.